The broadcast is now starting. All attendees are in listen-only mode.
Hello, and thank you for joining us. Today is our November 2018 webinar, Oil and Gas Use Cases with Seeq. Again, thanks for joining us. We will be taking questions during the webinar. Please go ahead and submit them via the questions section of the console. We'll be focusing on oil and gas use cases today using advanced time series data analytics. If you're new to Seeq, I encourage you to view our Introduction to Seeq webinar, which is available on our YouTube channel. And if you're interested in a live demo or have further questions, you can email us at info@seeq.com. My name is Jennifer Bensel, and I'm the Director of Marketing at Seeq. Today I'm being joined by Krista Novstrup, who is our Principal Analytics Engineer. She will go ahead and cover these use cases.
Thanks, Jennifer. Welcome, everyone. I'm happy to talk to you today about several oil and gas use cases. As an overview for today, I'm going to start out and cover just to set the scene with what is our reality working with process data and time series data, talk a little bit about what does an analytics solution look like, and then spend the focus of the time on the actual use case examples. You can see I have a number of them listed there covering upstream, midstream, and downstream. Our process data reality starts with the fact that we have a lot of data. We have historians, they're full of all of this time series data we're collecting. In addition, we also have contextual data sitting in our business systems and our manufacturing systems, all at the ready for us to be able to analyze. Our difficulty comes in the tools that we have to do that analysis. Oftentimes, we're in tools that make it difficult to really bring together the multiple pieces of data as well as be able to actually manipulate that data. So in the middle there, you see Excel. That's one spreadsheet application that people use, and there's others. So when you think about how it is to collect that data, contextualize that data, do your calculations, your cleansing in those tools, they're not optimal. As a result, it's hard to find good return on investment. We lose time in work processes around these inefficient tools and the ability to get information from them. And so how do we take that and look at driving better business outcomes? What does an analytics solution need to look like to improve that whole work process? I'd like to start by looking at the right-hand side of this, where we have decisions, actions, profitability. That's our ultimate goal on what we want to be able to achieve for the business. Where does that start when we talk about the data that we have? That starts on the left-hand side, where we want to be able to do diagnostics on that data. We want to be able to do predictions from that data. We want to be able to have self-service analytics for engineers to be able to go in, make sense of that data, and then use that to ultimately drive those decisions and actions that we do in our business. You'll notice down the middle of the screen that I have a number of different boxes here, though, highlighting key elements that need to be in place for us to successfully do this. It's not sufficient for the engineer to just have a tool to look at the data. It's how do they take and communicate that with the broader organization, thinking about how we document, report, create dashboards to share this information. How do we capture the knowledge and be able to collaborate on these analysis and also implement it into monitoring types of applications. The next two slides look at what does an analytics solution entail, and specifically talking from the perspective of Seeq. So we've talked about, from an application standpoint, something that allows our subject matter experts access to that data, and then we can use that collaboration and sharing to spread that across our teams and to managers. The impact that we need to have from this application needs to focus on time to insight. So I mentioned traditional tools that we've used up to this point can sometimes be very time consuming and prohibitive on doing analysis. We need to have access to insights to be able to get at the relevant data that describes that process, and then being able to focus it on the right person for the right insight to be able to take action on that. When we talk about what data do we need to have to be able to get these insights from, that's our time series data. That's the heart of what we're going to be looking at. It comes from also analog signals. We have the industrial Internet of Things, Industry 4.0, numerous sources of data that we want to be able to bring together. And then finally, the heart of what you're going to see as we look at these use cases is how do we begin to apply analytics to that? Looking at big data, bringing all this data together. How do we learn from that data, machine learning, and then being flexible with the environment we do that in. From a perspective of Seeq, for those that aren't familiar with the application, this is a quick overview of what our architecture looks like. Seeq is a browser-based application that has two parts to it. You see that on the top of the screen. We have our workbench, and this is where you're going to bring your data in and do the analysis. A lot of the examples we're going to look at today are going to focus in that workbench environment and show you how we come up with those solutions. The second part of the Seeq tool is our organizer. This is where we can take that analysis that we've done and bring it together as a report or a dashboard for sharing with colleagues. And you'll see part of how that also plays into the use cases that we've put together. Just as a few other comments that I'll mention while on this slide for those new to the product, you'll see at the bottom of the screen a number of different data sources from which we can pull that data in. And that's a key element, as I mentioned, to be able to have all the information relevant to solve your problem, to ask your questions. So with that, I would like to move on to actually where I'd like to spend the bulk of our time today, and that's on talking about use cases specific to the oil and gas industry. The first use case that we're going to talk about is salt deposition corrosion. So in this one, the idea here is that we want to monitor what our salt deposition temperature is and where we're at to minimize corrosive events in our equipment. In particular, we're talking about, for example, in refineries, our crude unit overheads, our FCC fractionator overheads, or hydroprocessing effluent trains. The idea here is that by monitoring and understanding the amount of corrosion and risk we have for corrosion, we can use this to then minimize corrosive events. The solution that we've come up with here is to be able to take both our lab data that we've sampled and combine that with the process data that we've kept in our historian on how we're operating. You'll see on the next slide where we look at the salt deposition temperatures and we compare that to our limits. And ultimately, we want to identify and visualize high-risk periods. When we've done this, then our results are the ability to minimize lost production because of corrosion damages and minimize unplanned shutdowns from maybe accelerated corrosion events. Looking a little bit closer at the picture that I had on the previous slide, this shows an example of an analysis that was put together. In the middle of the screen, you see several signals. The one in dark blue is our operating temperature. You then see in lighter blue a salt risk alarm point where we're monitoring that. And then finally, in red, we have our max calculated salt deposition temperature. We're monitoring this through time. You'll notice that we have up near the top of the screen some red bars that are indicating when we're exceeding that salt risk alarm point. And we can take this information and ultimately calculate, in this case, a percent at risk, which you see on the bottom of the screen there. That percent at risk helps us understand where we're operating, and we can tie this back to how we're running the units. Finally, at the very top of the screen, we can take this and summarize this information, maybe on a weekly basis, as you see there, or on different periodic frequencies as needed. So that was our first example to get everyone warmed up and thinking about analytics in Seeq, the next example, we're going to take a little bit deeper dive and actually go into Seeq and see how the analysis was done. For this, we're going to look at heat exchanger fouling. The idea here is that our heat exchangers foul over time, and this results in reduced efficiency of the heat transfer. As a result, we need to take the units offline and we need to clean them. Historically, you may do that on a regular schedule, but that may mean that you're taking the unit down more frequently than you need to. Alternatively, you may try to get that unit to last longer, and as a result have to cut rate or have unplanned shutdowns because you can't meet the needed temperature change. So what we'd like to do with this example is monitor what is that degradation in performance, and then use that to predict when should we take the unit offline and do maintenance so we can schedule it into our plans. Our solution includes a predictive model that you'll see that we'll make based on operating conditions. And then another aspect, which we won't go into here, but is to recognize that we can also take and compare to past cycles to see when we may have accelerated fouling. Our result is that we are able to do this risk-based maintenance. It allows us to reduce production losses, contributing to savings in the tens of thousands per year, and really allow us to plan optimally when we do that maintenance. As we look at this, a couple things I want to keep in mind as we talk through how we do this solution. And the first one is some key questions to ask as you're doing a solution. First, what do I want to know or optimize about the process? In this case, we've already described we want to, for the heat exchanger, watch what the fouling does over time and see how that degrades our performance. The next question is, what physical and engineering models exist? Oftentimes, we can either use these models or they can inform our approach that we may take as we do our analysis. The last item is, what data do I have? In an ideal world, I have perfect instrumentation around my system, and so I can go and apply all of those physical and engineering first principle models I have. In reality, I may not have all that information, and so that might modify the approach that we have to take as we do that analysis. Some additional things to think about as we look at the solution that you'll see is around how we actually do the analytics. The first one is data cleansing. Thinking about, before I go and I do my analysis and create that predictive model, what types of data cleansing is relevant? Maybe I have invalid data that I need to remove. Maybe I have noisy signals to smooth, or I might have missing data, and what do I do in those cases? We already talked about what the model form is that we'll consider, so whether we can apply first principle models, maybe we need to do something of an empirical basis, and then also leveraging rule-based models to look at different operating modes, for example, and focus in how the model fits to those scenarios. And then the last item there is historical benchmarking. How do we take advantage of that historical data and use that to inform the current analysis that we're doing? So with that, I'd like to show you how we've approached this solution in Seeq. I've started here in my Seeq workbench analysis, and I've loaded in my relevant data. I have my hot and cold liquid flows and also inlet and outlet temperatures. I've broken this analysis down into several worksheets, and then you'll also notice that I'm going to leverage my journal to help walk through this this analysis. I'm going to go to my calculations tab, and my first step is to calculate some relevant parameters that describe the fouling. I'll start by looking at my hot duty as an example. I'll open this up in formula, and you can see that I can use Seeq's formula to calculate my hot duty for my flow rate, specific heat, and my outlet and inlet temperatures. I can repeat this for my cold duty. I can also calculate my log mean temperature distribution, and other relevant parameters to ultimately calculate then my heat transfer coefficient from my surface area, average duty, and log mean temperature distribution. Once I have this heat transfer coefficient, now I'm able to proceed with my analysis. Before we get to modeling it though, we want to talk a little bit more about data cleansing. I'm going to go ahead and on the screen here highlight for you my original signals in orange. You'll notice that there's periods where I have some big drops in the data where I potentially had a short downtime event, and I'd like to exclude those from my analysis. I've identified those periods in this case using Seeq's value search to look for when the cold liquid flow is below a certain threshold. In addition to removing those periods of time, I have additional outliers that I may want to remove, as you see here in this top signal. And so I'm able to use Seeq's formula to remove both those downtimes and outliers. Now that I have my cleansed signals, I can move on and go to my modeling. You notice I've put my heat transfer coefficient at the top, as well as the signals I'm going to use as inputs to the model. I've added one here called days in service, and this is where I want to look at how long have we been operating. In this case, I've made a 1-day signal, I remove my downtime periods, and then I sum it across the cycle to understand how many days it's been that this unit's been running. With these inputs, I can now bring up my models. I've made several different versions with varying input variables. I'll go ahead and open up this one here where I have 3 input parameters. So I've modeled my heat transfer coefficient with days in service, cold liquid flow, and cold outlet flow. Notice my training window is set to 2020 in the future. As new data becomes available in my historian, it's read into Seeq and is continually updating my model. I've used a linear model and ordinary least squares. I have an option to filter my data down to look at a specific operating mode if I want. In this case, let's look at all of the data during that time period. Here I have my coefficients from the regression. You can see my statistics around this regression shown here. In addition to seeing the statistics of the model, in Seeq I can also pull up my scatter plot to be able to see if there's any additional red flags in here on whether this model is good or not. That looks nice and random, so let's continue on with this model and do our predictive maintenance. I've now brought up a display where I have my heat transfer coefficient, and I've predicted it into the future for 2 scenarios. 1, a high cold liquid flow rate, and 2, a low cold liquid flow rate, as you see in the gold and the blue. This gives me an idea of the impact of my operating conditions on my maintenance prediction. I've highlighted that with a capsule, and down in the lower right hand corner I can see that my range is from November through March when I need to take this offline, depending on how I operate my equipment. My final step is to take this result and put it in an organizer topic so I have a report here that I can share with others in my organization. I've included some statistics along with that chart. To share, I can take a presentation link, and this URL can be mailed out to my colleagues, and they're able to bring it up in their browser and then see this report. So that is the end of our heat exchanger example. I'd like to pause at this point in the webinar and ask if we have any questions so far. Jennifer, has anything come in?
Not at the moment specific to use cases. If there was a question we haven't been able to answer online, we will follow up with you after the webinar is completed.
Excellent. I will proceed then. The next example I'd like to look at is well completion analysis. The idea here is to optimize well completion across thousands of wells. The idea is wells interact with the reservoir and other wells, requiring lots of engineering expertise and calculations to be able to monitor operations. And so we're going to leverage Seeq to be able to provide that input to the engineers. In particular, in our solution, you'll see how we're going to identify well stages. We're then going to look at some specific parameters. In this case, we're going to calculate a delta between the instantaneous shut-in pressure and then also a settled pressure following that completion. We'll then be able to track the delta pressure over time, and then we can scale this analysis across all wells in our enterprise. As a result, our engineers are going to be able to use this information to optimize how they operate. In this video here, I've started in Seeq Workbench Analysis again, and we will once again leverage the journal feature to walk through the analysis. I've loaded my signals, including a treating pressure on top, my slurry rate, and then also a signal that represents which well is active. This is on a zipper unit, meaning I have multiple wells which are feeding into the same signals. Our first step is going to clean the data. In this case, I'll bring up my clean signals and open up one to show you what we've done. Here, we've used a valid values function. This allows us to filter out any invalid data which may impact the analysis as we proceed. Our next step is to determine when well 1 is active and focus our analysis on well 1 to start. I have found these periods in time as indicated here at the top of the screen by the bars, and I've done this using Seeq's value search. So I'm looking for well 1 active. I'm able to search my active well clean signal for those periods when it's equal to well 1. Next, I'd like to understand during those well 1 periods when I'm operating at high pressure and at a high slurry rate. So you see a number of capsules at the top of the screen that we've created. I'll zoom in to highlight those. In particular, you see where I've identified high pressure periods and high slurry pumping periods, both with my value search. And then finally, I've identified my well 1 stages that we'll focus our analysis on in brown. In order to do this, I leveraged formula and I used our intersect formula to find the intersection of when well 1 was active and I had slurry pumping and high pressure. I'll zoom in now to one particular event, and you'll see here what I'm most interested in is at the end of this well completion, what my pressure does. And I'd like to characterize this curve. To do that, we need to first identify this time period so we can focus our analysis on it. To do that, I've created a capsule here. This comes from a condition called post-stage, which I made using formula. In here, I've used my after end function to create a capsule that is 1.5 minutes long at the end of each well 1 stage. Now that I have this capsule, I can focus my analysis on this post-stage period. The first calculation I'll do is to calculate an instantaneous shut-in pressure. To do this, I'll use my signal from condition. In particular here, I'll look at that treating pressure. I'm going to take an average across that post-stage period, and that's what I'll define as my instantaneous shut-in pressure. I could alternatively use other various statistics here to identify and quantify what the pressure is doing during that particular capsule. The next thing I'll do is I'll calculate the end pressure, once again using that same signal from condition tool we just used to calculate the instantaneous shut-in pressure. Finally, I can take and calculate a delta between those as the item that I ultimately want to monitor. Here I'm taking the delta between my instantaneous shut-in pressure and the ending pressure. The last view that I show is to broaden this out from one event to all of our events and be able to scan through time. Once I've done this, I can look for trends, I can identify outliers, and I can do further investigation. The next example we have is water hammer detection. The idea here is to minimize water hammer events following an emergency shutdown. In particular, rapid valve closures during the emergency shutdown can cause water hammer, which can lead to mechanical damage and safety issues. Detection of these events can inform how we re-engineer and design the emergency shutdown equipment. For this solution, we're going to detect water hammer in our pressure measurement, but by identifying pressure waves with a certain periodicity and amplitude decay and proximity to an emergency shutdown event. We can quantify the event duration, amplitude, and frequency as we desire, and then we can monitor over time. The results allow us to enable a focused redesign of the equipment, which can reduce the number of water hammer events when we have an emergency shutdown. We're able to do proactive management to reduce damages and releases to the environment, and this ultimately reduces maintenance costs and production losses, which can easily be $2 million per day for downtime. Before proceeding, I'd also like to mention, in addition to this particular example where we're looking at emergency shutdown events that are leading to water hammer, another area that you see this in is hydrate formation when you look in both upstream and midstream applications and want to characterize this same type of event. For this example, I will once again go into my Seeq workbench analysis, and I've started here with my relevant signals. I have my water pressure, and then I also have a condition that's identifying when I have an emergency shutdown event. Here I see normal operations. I have some sort of process upset, and that triggers my emergency shutdown. During the emergency shutdown, I then may have a water hammer event. Let me zoom into this water hammer event for you to see it up close. Here you can see that ringing in the curve, this nice periodic decay of the signal. This is what we'd like to detect in our equipment. To do this, I'm going to go to my next worksheet page where I've written out in my journal the steps for this analysis. In particular, for this analysis, I could consider using a profile search. We're going to take a little bit different approach today. I'd like to focus on looking at being able to determine when we have these events independent of a specific amplitude or periodicity. To do this, our first step is going to be to take a first derivative of this signal. I can do this using formula, and then you'll notice I also put a remove outliers on here. This was to handle any large values created by discontinuities in my signal. By taking that derivative, it now allows me to easily identify the positive periods during my water pressure hammer event here, as you see me highlighting with my cursor. I do this by using Seeq's value search, and I take that pressure derivative and I just look for when it's greater than 0. You'll notice when I look at the capsules that form this, during the water hammer event, they're very evenly spaced. When I look at a period that's not hammer, you see that they are irregularly spaced because they're just representing the noise in the signal. This is going to play to our advantage as we look for that water hammer event. Our next step is to create what I call the water hammer equation. This equation is going to be created from signal from condition, and we're going to look at our water pressure and look at the range over which it changes during each of these positive portions. And then we're going to plot this point at the start of each one of those capsules that represent the positive portions. This allows us to do two things. One, I can easily see now how my amplitude is changing over time during this water hammer event. The second thing that you'll notice is you can see I have a signal that clearly represents unevenly spaced points during just regular noise in my signal, and then very evenly spaced sample points during that water hammer event. We'll use this to our advantage. My next step is to create a signal I call running interval. In this formula, we do two things. We take the interval, that means calculate the difference in time between each set of sample points, and then I'm going to look at a running delta of those differences. Because our water hammer sample points are evenly spaced, a running delta of those values will always be at 0 or close to 0. When I have unevenly spaced points, you can see that they are not near 0. This allows us to go to our final step, in which we'll detect the water hammer event. Here I've once again used value search to look at that running interval signal and looked at when I have values that are near 0. Here it's then highlighted that water hammer event. As a final step, I can go look at additional periods in time to assure myself that I'm not picking up false positives. For example, here's the data from the upset. I have a periodic, an oscillating signal, but it does not have that same periodic frequency that my water hammer event has. And so you see, I'm not picking up any water hammer events here. With that, I'll move on to my last use case. And instead of being a specific example in Seeq, here I'd like to comment on how we think about using Seeq and integrating it into our workflows. So for example, in the heat exchanger use case, you saw how we took those results and incorporated them into a report that we shared at the end of the example. In this particular use case here, the idea is to be able to leverage a remote technical center of excellence to help out with reporting. The idea is site engineers are very busy and have a number of things on their plates with which they need to do. And so enabling something like this allows those site engineers to be able to be freed up to focus on actually resolving action items instead of all the initial pulling and analysis of data. In order to be successful at implementing something like this, you have to think about a solution that allows you to create these transparent reports, to be able to have our KPIs and our visualizations, a solution that allows collaboration and integration with the analytics. As a result, when you bring these things together, you get a consistency in analysis across your various sites, cross-site learnings, and quicker time to resolution of your action items. As I near the end of the material I have prepared, I wanted to just highlight once again some different enabling capabilities that we've seen throughout this webinar. One of them we looked at was data cleansing. We saw this both in the heat exchanger example and in our well completion analysis. The second thing I'd like to highlight as an enabling capability is the tools that you have to do advanced analytics. We looked at this in a couple different ways. We looked at our predictive tool with the heat exchanger example, and then we also saw with the water hammer example some creative ways to be able to identify and find various patterns in our data. We've talked about the importance of reporting the results, and then finally how this feeds into an analytics workflow and thinking about how we're able to take and share this information to ultimately help the business. So my final summary slide I would like to leave you with is to think about how do we transition from reactive analytics to predictive analytics, to prescriptive analytics, and ultimately profitability analytics. As you see in my display here, the first thing is to leverage the existing data. And that's what I hope you saw by our ability to bring in data from multiple sources potentially. You look at the salt deposition example, we brought in our process data as well as lab data to be able to analyze that in one location. The next step is the ability to apply those advanced analytics. And then a key part is how do we enable personnel? And so you saw some collaboration there and how we are able to leverage the reporting functionality in Seeq. And ultimately, as we put all of these pieces together, that allows us to optimize our business, as we talked about at the beginning, on driving actions and decisions and ultimately profitability. With that, I'd like to once again open it up to questions. Jennifer, have we had anything come in?
Yeah, we have two questions. The first one is it possible to get your customized report emailed to you on a regular basis, say a weekly basis, or on a conditional basis, for example, if a certain KPI gets out of bounds?
Mm-hmm. Currently in Seeq, we do not have the functionality to have the report emailed out. Next year in 2019, we will be adding a notification capability within Seeq so that you can be alerted either on a regular frequency or on that as needed frequency for an event occurring. That said, today we're able to leverage various notification capabilities that come with other software that you may be using. An example of that would be the use of Pi notifications if you're an OSI Soft Pi customer. So we'd be happy to talk to you more about that.
All right, and the second question is, who is the owner of all the data collected? Do you cross it with other clients' data to have better models?
If I understand that correctly, so Seeq, we're not collecting the data. Your data stays at your site with your company, so we're not comparing across customers at all to build models. Within a given customer, though, there is the ability to bring in data from multiple sites, and so they can compare across sites. If that was not the exact direction of the question, please feel free to follow up with us, and I'm happy to talk with you further.
And I have one more question. For the predictive model, how do you choose the model type, for example, linear or polynomial?
So part of it is an understanding of the process that you may bring to it as a subject matter expert. That said, if I have limited knowledge, I typically like to start with linear and then see what that gives me. And if that doesn't appear to be sufficient, that's the point at which I will start to look at other model forms. The same goes for a regression method. So In this example, we used ordinary least squares, but Seeq also offers ridge regression and principal component regression. And so if you know that your input variables are highly correlated, you can immediately go to those other regression methods. But I'll typically do a first pass and start by looking with ordinary least squares. Any other questions, Jennifer?
Yep, not at this time. We're done. Thank you.
Okay.
All right, well, thank you, Krista. And if you guys have any additional questions, please feel free to contact us at info@seeq.com. And as always, we encourage you to connect with us on social media and visit our Seeq University on YouTube to get more video tutorials. If you have any other questions, again, you can email us, and that concludes today's webinar. Thank you for attending.